I'm a very big fan right now of the increase in interplanetary smallsats. So you may have heard of the Mako satellites that went to Mars last year. Two little tiny briefcase-sized satellites that no one expected to work, yet both of them worked better than expected. Gave us the beautiful photo of Mars, communicated with the InSight lander as it went down, and got rid of that horrible silence, blackout silence during the descent stage. And so I think those two satellites have really opened up new avenues for people now who realize that maybe interplanetary smallsats and CubeSats could work.
We're back with another episode of the Cold Star Project, and we're focusing on small sats and space this season. And I wanted somebody on who was from the academic field, had some experience out there in the world. And I don't just want business owners here. So this is Amelia Greig. She is, well, originally a doctor. She's a doctor in plasma physics and electrical propulsion. So you all better watch out, from the Australian National University. Got a postdoctorate in plasma physics at CalTech, and then took teaching positions at California Polytechnic State University, and has moved to the University of Texas at El Paso Center for Space Exploration and Technology Research. That is quite a mouthful. Thanks for being here, Amelia.
Yeah, of course. Thanks for having me.
You bet. So tell us what's going on at this big words phrase, Center for Space Exploration and Technology Research.
Yeah, so we get around the big name. We call it CSETA.
Okay.
Yeah, there's the little acronym for you. So it's a center dedicated for space exploration and technology research, hence the name. Right? There's a bunch of different work going on there, focused on, say, propulsion systems, energy development, or energy systems, unmanned aerial systems, small satellites, autonomous systems. So plenty of things going on. It was developed as a NASA Mirror Center, so that's a center that's partially supported by NASA to try and help build up expertise, particularly in areas that are minority serving, so trying to increase minority participation in the technical fields, which is great. But it's a university center doing amazing research in all these different fields. So, we have on the propulsion side of things, there's a lot of work going into Methalox rockets, which is what we could use to bring crewed missions back from the surface of Mars without needing to take all the propellant there, for example. Smallsats, we're developing a smallsat bus of our own that's capable of doing pretty much any scientific payload or propulsion testing or anything like that you want to do on orbit. Energy research is focused a lot on combustion energy, moving a little bit into renewable energy sources as well, of course. And then there's the unmanned aerial systems for traffic management or long-range endurance vehicles, things like that.
Okay. So what part are you specifically getting involved in?
Yeah, so my part specifically is the small satellite project and micro propulsion systems. So small satellites, we're developing the bus, like we said, we're hoping our first couple of missions are all based around doing on-orbit manufacturing. So we're trying to show capabilities or technology demonstrations to show how we can improve on-orbit manufacturing or do on-orbit manufacturing for satellite repair, servicing, construction, anything like that. So we're developing a bunch of satellite missions that are doing those kind of things. On the side of that as well, developing micro propulsion systems. So my background is primarily electric propulsion. So bringing in a bunch of systems that I've worked on previously, electrothermal plasma thrusters, electrostatic plasma thrusters, working with external partners such as Air Force Research Lab, for example, to develop these into flight-ready systems and see if we can actually get them launched and working in space properly. One big aspect that I focus on with the micro propulsion side of things is actually putting them into the spacecraft and how they're going to work once you put them into all the rest of the subsystems. A lot of people, not everyone of course, but there are a lot of groups out there that just develop the propulsion system or just develop the satellite. And then CubeSats, of course, microsatellites tend to be plug and play. So you take one and you put it in. That can sometimes, especially with electric propulsion, where you're depending on certain potentials and certain ground situations to be happening, can change the way that the propulsion system behaves, or it can then change the way the rest of the satellite behaves. Like it might interfere with your communications through high voltage spikes and things like that. So focusing on actually taking the propulsion system and putting it into a satellite.
Okay. And 20 odd years ago, I was designing power plants, and power quality factors were important then, and it looks like they're still important today. On a
Absolutely.
smaller scale. So how many people are involved in this? I take it you've got some graduate students that you're leading?
hmm Yeah, so the small satellite side is we're developing. We've probably got 20 or so people working on that right
Wow.
now. Bunch of different projects. So that's,
Hmm.
sorry, the small satellite and the micro propulsion stuff has probably got about 20 students or so working on it right now.
Okay.
We're expanding all the time.
Yeah. And so do you have an internal sponsor at the university that you go to for funding on that, or organization, or how does that work?
So we try and form partnerships with different like commercial entities or
Mhm.
other like government institutions, things like that, that would benefit from us joining them in some
Mhm.
kind of project. So like I said, we're a NASA Miro Center, so there's some support coming from NASA. We work closely with Lockheed Martin
Hmm.
on a few of the projects. One of my projects, I'm working with Air Force Research Lab, for example. And so, yeah, we bring in external funding. We, competitive grants or contracts, anything like that.
Right. Okay. And how long are these projects running for? The graduate students are there for what, a couple of years or something like that? And how much of that time is spent working on this kind of project?
Yeah, so the graduate students, they will often be doing their project for their thesis.
Mm.
We tend to try and pay them as well. Obviously, you need
Mm.
to, support your students. So they're working on average about 20 hours a week for us on the project, which quite often overlaps with what their thesis ends up being. We also have some undergraduate students that work for us as well. Again,
Okay.
we pay them, and that's their part-time job rather than working at McDonald's or something like that. It's a
Beats
much better
McDonald's.
experience for them.
Right. I agree. Okay. Feel free to get a little technical on us. I'm curious. I mean, I don't know if you've got NDAs with folks where you can't talk about it, but if you can, I'd love to hear about some of the technical issues that you've run into developing these propulsion systems or the bus.
Sure. So I'll tell you about one propulsion system that I'm working on right now. It's called Pocket Rocket. It was
Okay.
actually the propulsion system I worked on for my thesis, my PhD thesis back in Australia, so developed by the Australian National University. I sort of brought the technology with me when I went to Cal Poly, because they have a very established small satellite program.
Hmm.
So it seemed like a great opportunity to try and put it into a satellite and try to launch it. So I had a bunch of students working on it. We developed like the propellant feed system, so you could store it at high pressure, regulate it down to low pressure and the right flow rates to go through the thruster. We developed a power conversion system or power processing unit. So you go from the 4-volt DC current that the spacecraft batteries will
Hmm.
provide you, and we had to convert that to a 240 volt peak to peak, 240 volt peak 13.56 megahertz radio frequency signal.
Okay.
Um, so we developed that, and then put all that into a CubeSat structure with the thruster. Right, thruster wouldn't turn on. It's
Huh.
like, oh great, what happened? So we took the thruster out of the structure and just sat it there with the feed system and this power supply, and the thruster turned on.
Hmm.
Okay, what's going on here? Put it back into the thruster, into the CubeSat. It just would not work when it was
Hmm.
inside the CubeSat structure. And this comes back to the fact that electric propulsion systems tend to be very finicky when it comes to electrical components. So there
Right.
was too much grounded area
Hmm.
on the spacecraft, and it was just throwing off the way that the thruster operated. So you can get around that one of two ways. You can put it in a non-conductive structure, or you can just separate it, like isolate it a little bit.
Hmm.
But because it's electric propulsion, the plasma itself is a conductive gas, and so it's not as simple as just putting in like an insulative material
Hmm.
to stop direct connections. The gas still makes the connection with the outside of the
Hmm.
spacecraft. So
Okay. So lots to learn. About
mhm.
how long does a turnaround like that take where you're like, oops, this unexpected thing happened and we've got to disassemble the whole thing and check it out and then reassemble it and test it again?
This one didn't really take that long. It was only probably a couple of weeks before we got it working. But that was because mostly I was so familiar with this system, having worked on it at that point for about 6 years. And so it kind of immediately clued onto what it possibly could be,
Right.
like looking at the only variable that changed
Hmm.
was basically how much metal structure you've got.
Right.
And knowing how the plasma behaves, I clued onto that pretty quickly. And so we knew just cover the outside of the CubeSat structure in some kind of dielectric to cut off that conduction. And that seemed to work okay.
Okay, cool. So now these projects, you kind of get a budget and a scope and all that. Have you run into any scope creep as you've gone along?
I tend to have had the problem of not enough budget to do what we want. So the scope becomes a lot more narrower as you go through. Or there can be occasions where you just do giant sidestep and start looking at other things.
Okay. And then obviously, I mean, you make these things and they need to get launched somehow. How does that process work where you're finding a launcher and interfacing with them?
So right now, the main way that universities get CubeSats into space is through like the Educational Launch Initiative, which is organized by NASA, CubeSat Launch Initiative. So they basically put out a call, usually it's every year at least, and they just say, if you're a university or other educational or like low profit, entity, and you have a CubeSat mission that you want to put into space, then tell us about it. And if we think your science is right or the technology you're trying to demonstrate is useful, and we think you can actually make this work, then they will provide you a free launch as a secondary payload on another mission. So when you have the big rockets, for example, launching the big satellites, there's always little tiny areas around where you can fit, say, like a little tiny CubeSat like this. So they just sort of tuck us away. Usually it's right down the bottom of the upper stage, right near the engine. So lots of vibration, lots of noise, things like that. But you just build tough satellites and then you can slide them in there.
Right. Okay. And how does the scheduling for that work? Because they've got their launch date, and then a common problem that has come up with smallsat development from anywhere is that insufficient time has been left on the back end for testing, right? And that gets really scrunched and rushed, and then, okay, we put it in, and then you get this horrible 40+% failure rate, partial and full mission failure rate. So how do you deal with that?
Yeah, that's a really tricky one. And if anyone ever figures out the answer to that, I'd love them to let me know. But in my experience, all of the satellite projects I've worked with have been through universities. So you're not only dealing with the fact that things always take longer than you expect, even if you're a professional engineer, but you're also dealing with students learning the process as they go, senior students graduating, new students coming in, things like that. So maintaining a good knowledge transfer through the process helps. Building time into the schedule to give you a buffer, knowing that things like students leaving is going to happen. But even then, there's always a mad rush at the end to try and get things finished.
Okay. Do they ever move the launch date on you, or does that stay pretty much a constant?
They would never move the launch date at the request of a secondary payload, but occasionally, as you know, launches slip due to various different, all sorts of things that happen. And so there has been occasions where we originally thought we were, say, delivering the satellite in January, but we actually didn't have to deliver it until April or May, and it just gives you a little bit of wiggle room. But you never know if that's going to happen, so you can't rely on it.
Right. It's just, kind of out of your control. Now, you mentioned the knowledge transfer, and this company is big on data collection, documentation, and that to accomplish that kind of knowledge transfer. And keeping a team that knows what they're doing is really important. There was a NASA paper where they interviewed a bunch of people about mission failures, and one of the things that the interviewee said was we were losing knowledge faster than we could keep it, right? So I'm curious what kind of processes that you've tried to capture this knowledge.
It basically all just came down to good documentation. Again, this is all based around a student, like university lab. So if you're a student coming in, and I'm going to talk about this from the perspective of Cal Poly, because I've only been at UTEP 2 months, right? So we're still trying to get all that stuff sorted here. But at Cal Poly, I was there a few years. And so the way they ran their lab, it's primarily undergraduate students. Few graduates, but usually it's actually like 90% undergraduate students at Cal Poly. And they are encouraged to come into the lab as freshmen. And so if you get them as freshman or sophomore, you know you've got them for 3 to 4 years. And you also know very clearly when someone's going to be leaving, because if they're a senior, then obviously they're leaving the next year. So they would, every project, the idea was the students kept as good a documentation as possible, but not many people like doing that. And it's a very hard skill to try and train. Even, I mean, I don't do it, and I'm their professor telling them to do it, and I'm not good at it. So, it's very hard to train that into people. But knowing that you've got seniors that are leaving, freshmen coming in, we tended to try and sort of pair up juniors and seniors with incoming students and transfer their knowledge. So if we had an orbits expert, for example, someone who knew the STK software really well, and we knew they were leaving, we would find any kind of new student coming into the lab that had an interest in it, even if they'd never seen it before because they're a freshman. And you just get them working on projects with the senior student and trained up that way.
Okay. And what media are you using? Are you recording anything on video? It sounds to me like having those paired off students recording a conversation on video might be useful for future. And I imagine things are being written down.
Tends to just be written down as far as I know. But yeah, you're right. The video idea might be a good one.
Yeah,
I've seen that done a few times. I've seen some students that were leaving and they didn't have time to find a replacement or something like that. And so they're like, you know what, I'm going to walk you through this procedure in this video. Done it myself a few times as well, so that you don't have to be there personally with them every time. You just like watch the video.
Right. Okay. So now I'm curious to go into what the course load and what the choices look like for students nowadays who are coming in and they want to be involved in space. And like, do they have a large range of choice, or is it just kind of you got what we offer and these are the slots? How does that work?
So I think a lot of that depends on the school. So I would say I did all of my education in Australia. And so I did my undergraduate degree was in aerospace engineering. And the school I went to, University of Adelaide, was a great school. But there's limited commercial aerospace in Australia. There's more now than there was when I went through, only like 10, 15 years ago. But there was some opportunities to get like hands-on summer internships or things like that, or do hands-on classes, building CubeSats, for example. That was not there so much when I went through. Okay. Coming over here, looking at Cal Poly as one example, they have so much choice at that school in terms of space. So there's the aerospace department. Every theory class at Cal Poly has an associated lab with it. So if you're doing your thermodynamics, you are also in a lab actually doing thermodynamics, not just learning about it. Space environments, propulsion, everything. And then on the side of that, there's the student clubs or the extracurricular projects and centers, like the CubeSat lab, where you can walk in there as a freshman and build something that's going to go to space and talk to, like, operate spacecraft that are already in space. There was a sounding rocket project, same kind of thing. The students would design, build, and launch their own sounding rockets. And having those kind of experiences as a student, I just can't imagine. So
yeah.
Same kind of thing here at UTEP, with the center, gives the students a chance to do the hands-on, actually developing flight hardware or payloads or prototypes or anything like that before they go to industry. There's all the different student clubs here as well. We're trying to start a sounding rocket program right now, but there's already like the Formula SAE. What else is there? There's the small satellite stuff, UAS, the unmanned aerial systems, UAVs. So.
Okay. Are there topics that students typically find more popular, like, oh, we're really excited about this, and okay, load up the classes for that?
I have found that, so my background being propulsion, I tend to be the person that teaches the propulsion courses. Every student, well, not every student, I shouldn't say that. There is a huge number of students that are interested in propulsion. I think a lot of that has to do with the visibility of rockets for launch vehicles and things like that. Like, these things are just huge. They're super impressive. If you ever see one in person, it's just an amazing experience. If you see one even on like video, it's still quite amazing. And so I think the visibility and the big noise, the big toys of the rockets helps with that. I taught space environments classes as well. And that's one where the students come in not really knowing what it's going to be. Like, if I space environment, people just think vacuum. Well, that's very boring. There's nothing going on there. But then you find out that there's actually these high energy neutrals that will literally rip apart your spacecraft, even though there's very few of them. They're super high energy. There's the plasma environment. The sun does all sorts of fantastic things. You know, micrometeoroids, orbital debris, all that kind of stuff. And so I found a lot of students, after they've done the space environments course, absolutely love that and want to get involved with it.
That sounds great. Let's imagine, let's put ourselves in the position of students right now who are coming towards the end of their graduate program. They maybe are concerning themselves with their thesis and finishing that up, and the rest of their coursework, there we are, and they're going to be graduated in a few months and that, right? Now I find I get hit up a lot by graduates who are like, hey, can I get a job? And I'm like, you have done nothing to differentiate yourself. I really would like to help you, but I need to, like, you're not just a interchangeable part. It's like, you are a little mini business now and you have to market yourself. So what do you think, what's your advice for folks who are about to graduate on how they can do something to position themselves better in the marketplace so that they get hired?
That's a really tough question. I would say if you are about to graduate, it's too late. You need to start thinking about this well in advance. Being involved in the hands-on projects like small satellite development or actual propulsion testing, things like that will, well, depending of course on who you're trying to get a job with, is going to help you. But a lot of people have that these days. So like you said, you need to set yourself above everyone else. So taking a leadership position is probably one good way to do that. I think anyway. I definitely look at leadership abilities, even if I'm looking for new graduate students coming in. I don't just want a 4.0 GPA. I want someone who's obviously technically minded, but someone who's very passionate with goals and has done things to show that they want to do this. So taking leadership positions is good. Having a and having a good network, I think, is really important. So one thing I did when I was a graduate student, and this was at the my supervisors kind of prompted me to do this. I took the opportunities. Being in Australia, there's very limited opportunities. So if we want to get jobs in aerospace, a lot of us look overseas, which is a shame, but you know, always intend maybe to go back one day. So,
there are a lot of space companies opening up in Australia.
Yeah, and now we've just got a space agency started up, and so things are really happening down there. It's really exciting. But when I was graduating, there was no hint of this whatsoever. It was either stay in Australia and do maybe something exciting every now and then, or come over here and build satellites. So I picked to come over here. But when I was doing my PhD, I kind of had that in the back of my mind. And so I would find conferences that I could go to internationally, like in America or in Europe, so that you could help get funding support to get over there. And then while I was over there, I would go to the conference and then I would spend a couple of weeks traveling around. I would just send emails to people and be like, hey, I'm visiting. Can I come see your lab, what you're doing? Can I give you a presentation on the work that I'm doing? Things like that. And so you just create these networks. Each network you create will give you like 5 more networks. And so I gave, I gave presentations in America, in the UK, mainland Europe, even Russia, Sweden, things like that. And so through that, developed this network that then found me the next job opportunities coming in.
And that is great. I was going to ask you to expand on what you meant by networking, because it's easy to say, but then what's an example? And you just gave a great one of going around. And not being afraid to talk to people. I think that folks get a little bit nervous about, and I'm connecting with PhDs all the time, like every day on LinkedIn. It's just great. And there was a period at the beginning of, oh my gosh, who am I to be, knocking on these people's doors and whatnot. But I found just about all of them are very friendly, and it's a kind of a collegiate atmosphere. Like, okay, we're all in this together. We're all working for the same thing. And if you run into an occasional grumpy Gus, whatever, I would just shake that off, because the effect of having 2 or 3 even of the right kind of people looking out for you, or being able to be a reference, or just even willing to point something your way is really invaluable.
Yeah, absolutely. I agree with that 100%. Yeah, and so, I mean, the worst thing that they can do, right? If you go ask someone, can I come visit you, or are you interested in hiring me? The worst thing they can say is no.
Right.
hasn't really changed anything. Like, yes, it's a little demoralizing at first, especially if they are a little bit grumpy about it, but you never know, maybe they're just having a bad day.
Right.
Really,
And I will stress that that is very, very, very rare, like maybe 1 in 200 or something like
oh
that.
yeah, no, I've never come across that myself, but I have certainly heard about other people experiencing things like that. So, but yeah, I mean, so they've said no. There's many other places you can try.
Right.
And, you know, and think
So,
about why they said no. If they say no, you can ask for feedback, and you
right.
can say, okay, can you tell me how I can improve so that it would be, you know, I'd be a more useful employee to you, that kind of thing.
Right. So yes, just being gutsy for a minute and being willing to reach out and developing that as a habit. It's a really good habit. And once you get into it, it just keeps going, and it becomes part of your kind of daily life. So I want to get your idea of what your vision is for you and the academic field for the next decade or so, maybe even the next few years. What do you envision happening? Where do you want to go?
Where do I want to go? So for me, I want to keep expanding the Smallsat program here at UTEP. So right now we tend to buy a lot of our components commercially and then put them together into a CubeSat and operate it that way. Whereas we would like to be able to develop our own flight computer and flight software and our own communication system and things like that. So that would give us, the reason to do that is that it gives you the most flexibility when it comes to working with science partners or technology partners who want to have a payload that they want to test. Then it gives you, it's a little bit more work to set up, but it gives you the most flexibility and eventual reliability when it comes to testing anything on orbit quickly and easily.
Right, because it's yours. Right.
Yeah, because it's ours, we can tweak it as how we want.
I was talking to Dr. Rick Fleeter yesterday, who has been around forever, and he was mentioning it. He's with Brown. Brown built a Smallsat for $5,000 because they made all the components themselves, and that's purely getting out of that headspace of, oh, a Smallsat has to cost $150,000, right? And what can we create ourselves, right? So it might take longer, it might take more money. So is that what you would say if I came up to you and said, Amelia, if I had all the money in the world to just hand over and say, okay, go make something, is that the direction that you would take it in, or would you go even bigger?
All the money in, well, that's a loaded question. All the money in the world, I would,
if you didn't have to worry
be doing
about it,
like crewed mission technologies, things for human exploration of the space system, space solar system, I should say.
Okay.
But if we're talking about small sats, I'm a very big fan right now of the increase in interplanetary small sats they're developing. So you may have heard of the Mako satellites that went to Mars last year. 2 little tiny briefcase-sized satellites that no one expected to work, yet both of them worked better than expected. Gave us the beautiful photo of Mars, communicated with the InSight lander as it went down, and got rid of that horrible silence, blackout silence during the descent stage. And so I think those 2 satellites have really opened up new avenues for people now who realize that maybe interplanetary small sats and CubeSats could work. So Artemis 1, of course, is launching soon. It's got a bunch of secondary payloads on board, which are usually, I think all of them are 6U CubeSats or something along those lines. And they are doing all sorts of scientific investigations around the moon just because they're easy to slip on as secondary payloads, but they're so useful now with the kind of technology development, miniaturization, things like that. I would like to see a CubeSat go to Venus. I think Venus is a planet that doesn't get explored much. Obviously, there's no chance of humans ever living on that planet.
There's a little pressure problem.
Right?
Yeah.
High pressure, high temperature, toxic atmosphere. It's not very welcoming. But I think it's very interesting in planetary science terms.
I'm not sure if we sent anything there. I know the Soviets sent a lot there. I mean, more recently.
Yeah, there's been US probes go. There's even one that went down to the surface, but of course they only last like 30 minutes or an hour before they disintegrate. But if you think about it, if you spent $500 million, so $500 million on this giant satellite, and you send it to a planet and it lasts like an hour, people are going to ask why. If you spend $2 million on a satellite to go there, And maybe it only lasts 15 minutes because it can't be as big and protected. But you just do 4 of those,
Right.
8 million, you've still got your hour long of scientific data, but tiny fraction of the cost.
Right. And if you stage them to go one after the other, maybe you can learn something and adapt during that
Or you could
short
send them to
period.
different parts of the surface
Right.
instead of just having one lander go to one point, things like
Right.
that.
I'm always amused by the memory of that one Soviet probe. The camera, the cameras wouldn't work, and then the covers wouldn't come off, and then the one time it did, at the end, it fell right where their probe was going to go into the ground, and they couldn't get in. So let's finish up here with where you would like to see micropropulsion systems go over the next few years.
Well, with the increase in small satellite capabilities and the interest in doing these interplanetary and lunar missions, kind of need these micropropulsion systems to work. And so there are so many options out there right now. Some are high thrust, some are really low thrust, some are really like high specific impulse, which means propellant efficient, basically tiny bit of propellant to do a lot of work. So I would really like to see the whole range of micropropulsion systems developed to do all of those different things, and then have them flown and have them tested and become just things you can take from the shelf, like these commercial off-the-shelf systems, put them in your satellite, send it off to Mars using a high thrust system, send it off to Mars using like a high specific impulse, low propellant system, put it into a Mars orbit using a high thrust system, and then control it using these really precision thrusters to point it the right way and things like that, and just have this become a normal thing. Right. About small satellites, whereas at the moment you have a small satellite with micropropulsion, everyone's like, "Ooh, is it going to work? Is this the one that's going to do everything?" And it's still very unknown. Launch providers get really nervous when you say you're going to put a propulsion system on your satellite because it's just so unknown. So I want it to become mundane.
Right, and make space boring is the slogan for Cold Star, the Cold Star project here on this podcast. So I love how that fits in. Well, Dr. Amelia Greig, thanks for joining us today.
Of course, it was a pleasure.
More engineers are not going to solve your problem. It's not a technical problem in that sense. It's a process problem. And the time to fix your processes was 20 months ago, and the second best time is today. This is Jason Canigan, the president of Cold Star Technologies and the host of this podcast, the Cold Star Project, which is all about identifying and solving process problems for space companies, because that's what we do.